Yes.
I'm not that.
Yeah. I'm very happy to be here. Yeah. Yeah, after class.
Yeah, I'm sorry, I forgot to post it. Actually, I worked on it and then I forgot to post it, so it's up on Canvas right now.
George.
Yes.
To see.
And of course, why would I?
Okay, singer. Okay. The other side singer.
I'm behind. No, side. Just. Just.
Okay, good morning, everyone. I think we're gonna start in about a minute or so here, so we're just waiting for a couple more people to join in here, so.
Yeah.
That's right.
All right, well, good morning again. I think we're gonna go ahead and get started. I apologize about the lab notes. I was working on them on Wednesday after class and I just simply forgot to put them up on Canvas. So I just uploaded them to Canvas right now. So if you look in Canvas under computer lab notes, you should see the set of lab notes number 3. And that's what we're going to be working with this morning. So I'll give everybody a second to download the electronic version of those lab notes so that you can follow along here. While people are doing that, are there any questions related to the material that we've been discussing this week? So just to review, we've talked about analyzing categorical data. We've talked about univariate and bivariate analyses of categorical data, including those design-adjusted Rouse-Scott tests. You're going to have a chance to work on those exercises for homework number 3, which remember is due on Monday. And then we talked about percentiles, we talked about subgroup analysis, and we talked about working with functions of estimates. So today in lab, we're going to see examples of all those different analyses we've been talking about over the course of the week. But before we jump into the labs, any general questions about the material or about your final projects as you're working on them right now? Any general questions? Yes.
So by direct correlation, what if we have the
Right. So if you're looking at an analysis where you're looking at the association of a continuous variable with another binary variable, there's a couple different ways you could do that. You could do the comparison of estimates for the 2 different groups defined by the binary variable, like we talked about on Wednesday. That's one way you could make sense of that association. Another way is you could fit a simple logistic regression model. If you wanted to treat that binary variable as the dependent variable, you could then use that continuous variable as a predictor. That's another way to do it. So those would probably be the best ways, but we haven't really gotten into logistic regression yet. But for those kinds of bivariate analyses, if you're just curious about the association between those 2 variables, you could just compare those 2 groups in terms of means. And that will give you a basic sense of the nature of that association. So. So it depends on what wall test you're talking about, but the Rouse-Scott test with the second order correction, the F version of that test is the most powerful test statistic that has been established to date. But there's many wall tests, so it just depends on what wall test you're talking about. So this is why Stata, as we're going to see in the lab, automatically prints the second order Rouse-Scott F statistic among all those other choices because it's the most powerful statistic. Okay, other questions about the concepts that we discussed this week? Any other questions? Yep.
There's in the code, there's that we are accounting for the weight. There are P weight and A weight. I wonder what's
Never use A weight.
okay.
I'll make that very clear. Whenever you're analyzing survey data, you should really never be using A weights. You might need them for some graphical commands here and there. In the book, we talk about using A weights to calculate population estimates of standard deviations as a workaround. But as a general approach, every single analysis command that you're using in Stata should be using P weights. There are cases where people have mistakenly used A weights in regression models or something like that. There was actually a pretty high profile media case where somebody was reporting on, I forget what exactly the outcome was, but it drew a lot of negative ire in the media and in the community. And when people went back to the code that this particular researcher was using, it turned out they were using A weights in all their code, and it radically changed their conclusions actually using the P weights. So just stick to P weights unless there are very special circumstances where it seems like the A weight would be necessary. Like we talked about with standard deviations in the book. So. Yep. Jupiter?
Yeah, I just wanted to ask, I think, 2 questions.
Yep.
The first one, though it may not be very necessary for the uncorrected chi-square,
Okay.
doesn't print the p-value for that, just for the sake of comparison. Instead, if I run for the assignments that we have.
Yeah, no, it won't print. So Stata does not automatically print the p-value for that because it doesn't want people to use that to make decisions, right? You could do the analysis with just the weights, but no other design correction to get that actual p-value. But again, like Stata does not want people to work with that. They're just showing that as a reference point to see what the raw distance measure looked like before you look at the adjusted test statistic. So if it was up to me, like I wouldn't even show that. Honestly, I would just show nothing but the right test statistic to report because people still ask questions about that. why is that in the output? So it's just meant to be a reference point.
The second one, I think, is on the degrees of freedom.
Yep.
If you can just perhaps recap, because when I look at the tables, like table 6.7 and table 6.8, on parameters of the routes for design adjacent test.
Yep.
For this, the first one, I see that it's easier to figure out the degrees of freedom, but I think maybe second one, you can just review just how.
Right, so let me bring up the lecture notes again. Okay. Okay. So as far as degrees of freedom go, this is what the degrees of freedom for that Rao-Scott test look like based on the first order correction. Okay. So what you see on this slide is where the degrees of freedom for the F test come from if a first order correction was used. Remember, if a second order correction was used, well, so again, just to reiterate here, under the first order correction, the numerator degrees of freedom are what we might think of for the standard chi-square. Rows minus 1 times columns minus 1. The denominator degrees of freedom are then rows minus 1 times columns minus 1 times the design-based degrees of freedom. So those are the degrees of freedom of that F test for the first order correction, which remember is not the default within Stata or R. Okay, it's the default within SAS. When you do the second order correction, where you're also scaling the generalized design effect itself by 1 plus the squared coefficient of variation of those eigenvalues, okay, that makes the degrees of freedom computation even more complicated. And we didn't show the formula for that because it's quite ugly, but that's what leads to the decimal degrees of freedom that you see in some of these examples. And you're going to see that for some of the examples coming from like the alcohol versus education example. You'll note those degrees of freedom are decimal. And that's because of the second order correction. It's no longer this straightforward calculation that you see here. The degrees of freedom are now a function of the variability in those eigenvalues, which is a non-integer value. Okay, so in that particular case, it may seem strange to report an F statistic with decimal degrees of freedom, but that's the correct approach to use. And that's going to happen again when you're using that second order correction that Stata uses by default. And in 2x2 tables, it's not as complex, but as soon as you get into 3x2 or 3x3 or something like that, that's where you start to see these decimal degrees of freedom. Okay, they're the same basic level that you see here. This is the essential information, but there are some additional adjustments that lead to those decimal values. So I can give, if anybody's interested in the exact technical calculation, this comes from our theoretical class on analysis of complex survey data. I'm more than happy to share those notes with you if you would like, but it's a little bit beyond where we want to go with this particular class. Okay, so Jupiter, if you'd like to see those, just send me an email and I'll send those to you. It's about a 3-page proof. So just take my word that that leads to decimal degrees of freedom. Okay. Good observation.
I've got a question. When looking at the chi-squared and the F test, here I see R-1, C-1 rows and columns. In practicality, like let's say we're using this and get a Stata or a SAS printout, or need to find the statistic. Do I need to, in practicality, do we need to calculate rows and columns, or is it just clusters minus stratum, like the normal variance of degrees of freedom when we're actually in use of it? Because I'm not quite sure how I'd
no, you don't have,
exactly.
Sarah, you don't have to do these calculations yourself.
Okay.
The software is going to print the degrees of freedom for you. Yeah.
Do that.
The key thing is not to report, for example, 1 degrees of freedom value for an F statistic. That's really going to confuse people.
Okay.
So the key thing is to draw from the output
Okay.
Yeah, the software is doing that calculation for you, including the decimal calculation that's involved in the second order correction. So.
Okay.
Other conceptual questions about what we talked about this week? Okay, let's turn back to the lab notes then. So hopefully everybody has had a chance to download those now. I apologize again for not posting them more timely. Okay, so just to kind of go over what the lab's going to cover. So we're really looking at examples of everything that we talked about this week. Okay, the chi-square testing, the categorical analyses, the analyses of percentiles, means, etc. Okay, so and we're going to look at different subpopulation analysis approaches as well. So we're really going to get to look at a variety of different procedures in the lab. So in the lab for today, both within Stata and within R. And this really gives you a sense of how many different possible functions and commands there are in Stata and R for the kinds of analyses that we were discussing this week. So you can see in R in particular, all of these different functions are part of the survey package, right? So survey offers a large number of different analysis functions that you can use for this kind of stuff. And we're going to go over those in detail today. So again, if you want to see more examples, more interpretation of the kinds of stuff that we're doing in lab, definitely take a look at chapters 5 and 6 of the book, where we provide more details and more examples of these approaches. Okay, so let's start with Stata. What I'm going to do is copy all of the Stata commands all the way down through log close into a new do file editor within Stata. All right, so in Stata, I'm going to go to Window, do file editor, and then new do file. And then paste those notes for today. Okay, so we should see all the notes. And some of you ran into this on last Friday. In Stata, all of the comments are going to be in green. Okay, so make sure you don't have any lines that are not in green, but still comments. Okay, because that can screw up your code as you're trying to run it. So comments in Stata generally will start with an asterisk, and that will make that whole line green. But if a comment wraps onto the next line, and it hasn't also had an asterisk added to it, that can make it look like regular code. And then when you try to run it, it causes errors, okay, because it's just words. All right, so just make sure about that. And the same thing applies to R as well when you're copying and pasting the code. Okay, so I'm going to start by setting the working directory where all the data sets are located within Stata, so that way I can easily access the NHANES data again. I'm going to open the NHANES data and clear out what's in working memory. So now I have the NHANES data set open within Stata here. I'm going to set all the variable names to lowercase again, just to make sure everything's easier to work with. And I'm also going to open up a log. Again, just good practice to have that log open while you're doing these analyses so that your results will get appended to that log. Okay, so that's what I'm doing with all those different commands here. So that log is now open, and everything that I do from here on out is going to be saved in that log as a part of the analyses. Okay, and I have all my variable names in lowercase. All right, so first thing we're going to do here is generate a 4-category version of age. So again, just another example of kind of recoding and important issues to be aware of. Remember how Stata handles missing data. So we want to make sure that we're not mistakenly recoding missing values into one of these different categories. So I'm generating a new variable called agecat4, and it's being set to 0 for everyone to start with. Then I'm replacing values on that variable with either 1, 2, 3, or 4, depending on whether these conditions are satisfied. And remember, Stata wants an ampersand, not the actual word and, when you're setting up these conditions. All right, then I'm going to tabulate that agecat4 variable with the missing option, which means that it'll show missing values as part of that tabulation. So I don't want to see any zeros, because if I see any zeros, that would indicate cases with missing data on age. That tells me how much missing data I'm going to have. All right, so I'm going to run these 6 commands all in one block here. And that's what I'm hoping to see. So age has complete data for all 9,756 cases. And now cases have been recoded into one of these 4 categories for age, for subsequent analysis. Okay. Okay, so hopefully for those of you who are Stata users, that recoding process is pretty clear at this point. All right, now, important for today's lab is how we go about handling subpopulations. So we spent a lot of time talking about that this week. Really, in my view, it's best practice to, before you jump into analyses, create indicator variables for the subpopulations that you're interested in. So this age 18P is a variable that's already been created in the data set to indicate adults who are age 18 and above. So adults there get a 1, everybody else gets a 0 on that particular variable. And it has, the subpopulation indicators have to be coded 1-0 within Stata. We talked about this with Isaac on Wednesday. If you have a subgroup variable that's say coded 1, 2, 3, 4, 5, and you're only interested in subgroup number 1 of those 5 categories, if I was to supply that as my subpop variable in Stata, Stata would treat all non-zero values as belonging to your subpopulation, which is obviously not what we want to do in that situation, okay? So always best practice, even if you have a 2 category variable to begin with, like 1.5 or 1.2 or something like that, create a dummy variable, 1 for your subpopulation of interest, 0 for everybody else to start with. And this applies to all the software, not just Stata. Just always best practice to create your subpopulation indicator in that way before you get into the analysis, okay? Being careful about missing data as well. So if I just look at a tab on this age 18P variable, I see that there are 5,864 NHANES respondents in that subpopulation, age 18 and above, and 3,892 who are not. And those are the younger children in this particular case. I want these analyses to focus on individuals who are age 18 and above, okay? But I don't want to delete the children. Okay, hopefully that point's clear with everybody at this point. Okay, correct.
If you don't specify that specific variable in those cases, you use the if, would it still treat it?
No. So you don't want to use if in the analysis command.
That's conditional.
When creating the variable, it's perfectly fine to use if to define conditions. But in the actual analysis commands, if you use if, you are invoking the conditional analysis. That even if you haven't deleted those cases yet, using if still deletes those cases. Doesn't throw them out of your data set, but for that analysis, it's basically the same thing. It's functionally the same thing. Never use if for these subpopulation analyses.
Data, because some data set they code it very different. How should we?
Yeah, so we talked about this on Wednesday. So when you're dealing with missing values on a particular variable, you have to think about whether that should be part of your subpopulation definition. Usually those missing values would get coded to a 0, so they don't belong to your subpopulation. And the way that Stata operates, Stata will process the subpopulation indicator first. So it won't throw away those cases with missing values from your analysis. It's going to recognize them as not belonging to your subpopulation that you want to focus on. So when you create that 1-0 variable, you can also account for missing data in the way that it's created by coding those missing values to be zeros. Or you can create a copy of that variable if your software is processing missing data first, unlike Stata. You can create a copy of that variable, fill in those missing values with arbitrary values, and then still create your 1-0 variable for who's in your subpopulation and who's not. That will prevent those cases from being deleted from the analysis just because they had missing values, even if they're part of the subpopulation definition or not. So that's the safest bet, is to work with a copy of the variable and a 1-0 variable at the same time when you're doing the subpopulation analysis, so that the missing values are not resulting in the same problem that we just talked about with George. Right? So that's the safest bet. Create your 1-0 variable, fill in arbitrary values for the missing values in a copy of that variable, and then work with the copy of that variable and the 1-0 indicator in your actual analysis. That's the most foolproof way to deal with missing value and your subpopulation. Yep. Of course, the better scientific way to deal with missing values is imputation. And we're going to talk about that later. But in the absence of imputation, you could just arbitrarily fill in those missing values. No, so again, key point here in this kind of analysis, cases with a 0 on the subpopulation indicator are still processed to recognize all of the sample design features, right? So we don't want to throw out cases like entire clusters, entire strata, something like that, just because they're not part of the subpopulation. So by assigning a case a value of 0 on the subpopulation indicator, that case will still get processed and read by the software when it's setting up for linearization. So if there's an entire cluster that has all zeros on the subpopulation indicator, that cluster is going to contribute a total of 0 to the variance estimation and not be ignored entirely. That's the reason why we code them all at 0. And that's what we talked about on Wednesday, is that Stata made the decision to process the subpopulation indicator variable first. It used to process the missing data first and just toss out those cases with missing values. Now it's the other way around because users were complaining, right? Because just because you had missing values, it was automatically doing a conditional analysis, throwing out those missing values. So again, code the missing values as a 0, as not being part of your subpopulation. And if you're using other software aside from Stata, create a copy of your variable that fills in the missing values to prevent that software from just arbitrarily deleting those cases. Does that make sense? Isaac? Yeah.
So, sir, we have system missing values in our server data set. So in one case, we get the system non-responsive result of like non-response. And secondly, we get the system missing value and so any particular person is not relevant.
Sure.
So is it the right way in both conditions we can impute the missing values?
You don't want to, well, again, we're going to spend an entire lecture talking about imputation. We're not there yet. You would not want to impute missing values for a not applicable item, right? So, and this happens all the time, believe me. We're going to talk a lot about this when we talk about imputation. But if I'm a male and I'm asked in a survey, how many times have you been pregnant? That's missing because it's not applicable to me. But there are analysts all the time who just impute like a black box. And all of a sudden, I'm a male and I've had 3 pregnancies, right? We don't want to do that because it's nonsense, right? So the best way to handle those kinds of skip values or not applicable values, just leave them as missing, like we were talking about before. You know, you might need to fill in an arbitrary value just to keep those cases in the data set. That's fine, but they would become a 0 on your subpopulation indicator. They're not part of the relevant subpopulation for analysis of that variable. Yep. So that's a great example, though, that can happen when you're doing these subpopulation analyses. You say, well, I want to analyze pregnancies. Males never get pregnant, so I'm just going to delete them from the data set, right? Makes perfect sense, right? But if there's a cluster, this is the key point about this entire discussion. If there's a sampling cluster that has nothing but males in it by random chance, that's perfectly reasonable, logical decision. I don't care about males in this analysis because I'm analyzing pregnancy. That perfectly logical decision can still screw up your analysis because there was a cluster that had nothing but males. And for linearization, if that's one of 2 clusters in the stratum, you're left with a missing standard error. And you've done nothing wrong. That's the issue, right? It's all about how linearization works and how those clusters are being processed for this subpopulation analysis. So the 1-0 approach is going to ensure that those are sampling zeros in that case. That's the key. So the not applicable question is a great example of why it's so important to declare these subpopulations. Okay. Any other questions about this?
Yeah, on that same note, I have a question. It's probably not line.
Sarah, you're really Sarah, you're really
address it later, but
it's very hard to hear you.
okay.
Really
Yep. I've got my earphones.
Go ahead.
If I have missing values due to ratios, So basically something where the value is either negative and it makes no sense, or there's a 0 for the denominator. If, for example, I wanted to keep them in the analysis, but I wanted to analyze them separately. So the continuous variable, but these values have meaning, but just not what they're giving me. Could you, let's say, put them a specific value, like make everything, in that case, -1, and analyze that separately? Would that be the best case?
Sure, that's a reasonable way to do it. And sometimes missing values are coded as like -999 or something like that. The key thing to do, and again, this is back to the subpopulation issue. The key thing to do is you either need to put those -999s as part of the zeros on your subpopulation indicator, okay? Or more generally, if you're not doing this kind of design-based analysis for linearization, you just need to make sure that those -999s are not included in the analysis of that variable, right? Because given that arbitrary code of -999, the software is going to think that that's just another numeric value. And that's going to figure into all of your analyses. So you either need to set them as zeros on your subpop indicator and focus on the subpop without missing data, or if you're not doing these design-based analyses, just set those to system missing values so that they're not actually included in the analysis. Okay. Everything we're talking about right now is how we would deal with this in a design-based setting.
Okay. Okay, thanks.
Good. This is all good discussions because, again, this is a subtle but important issue when you're defining subpopulations, especially with missing data. Okay, so we have this subpopulation indicator already defined. That's the key point here. I'm not doing this on the fly. This 1, 0 variable already exists in the data set, and for the sake of our discussion we were just having, let's suppose that the zeros also include cases with missing values. They just don't fall into our subpopulation. That's not the relevant case here, but let's just assume that's the case based on our discussion. So we're still processing those cases, but they're not going to be included in the analysis. Okay. All right, so here's our subpop indicator. Let's go back to the do file. Now we're going to set the survey design variables using survey set, and then look at that distribution again across strata and clusters using SPY-DES. Okay, so this is nothing new here for NHANES. We're just setting the cluster codes, the weights, the exam weights, and then the stratum codes, and then looking at the tabulation. So we've seen this already before. Again, key thing to note here, we don't have balanced repeated replication as an option, okay, given this sampling error calculation model, because some of the strata have 3 cluster units as opposed to just 2. Okay, so 31 clusters, 14 strata, about 314 observations per cluster on average. Okay, so let's start with some subpopulation analyses, again, being unconditional in the way we do this. So what I'm doing here in this set of 4 analyses, I'm looking at descriptive estimates of the mean systolic blood pressure. This is BPX SY1. Okay. First of all, I'm doing that overall for the adult subpopulation. I'm not using if. I'm using the subpop option as a part of the SPY modifier. Okay, that indicates this unconditional kind of analysis. I'm not deleting those cases with missing values or that are not in my subpopulation. I'm still processing them. That's the key. They're just not being used for the actual estimation. They want to make sure everybody's got that point. Okay? So I can do this overall for the adults. Okay, so when I calculate that overall mean, it's going to take a second here the first time it runs this. Okay, let's take a look at this output again. Again, I'm doing this unconditionally, so I see an exact report of the subpop number of observations and the estimated size of that subpopulation. Okay, so total population, about 288 million people. Adult subpopulation, about 213 million people. Okay, so I see the unweighted number of observations, the size of that subpopulation, and then so forth. If I had done this conditionally, let's just look at it as a contrast. Okay, if I had done this conditionally, I would say survey mean BPX SY1 if age 18P is equal to 1. Everybody see the contrast? That's the conditional analysis approach where I'm deleting the children. Okay. Now, this is a big enough subpopulation where I'm probably not going to have an issue with empty clusters, but look at the output in contrast. Okay. It thinks that is my population, period. The other 70 million people never even existed. And if some of those 70 million people come from entire strata or clusters, they're lost in the eyes of the software. Everybody see the difference? So I'm explicitly recognizing my subpopulation by using that subpop option. Okay? I'm still safe. I still didn't lose any clusters, didn't lose any strata. I get the exact same estimate results. I got lucky. You will not always get lucky. Okay, taking that conditional approach. This case, I got lucky because it's a big, very common subpopulation. Okay. Okay. Now, let's look at that same adult subpopulation separately, unconditionally, for each of the race ethnicity groups. Okay, so again, I'm focusing on adults, but I'm adding that over option to repeat the descriptive estimation for each of those different race ethnicity groups. Okay, so I'm adding over to do that. And again, this is all doing this unconditionally without deleting the other cases in a particular subgroup. Okay. So 5 different categories of race ethnicity. And for each of those, I see the weighted estimate of the mean, the linearized standard error, and then a 95% confidence interval for that mean. Okay. And again, an echo of the size of my subpopulation based on what I input the subpop here. Okay, if I want to look at design effects, I can say estat effects after running that command. If I want to look at, one second here. Okay, so look, if you look at this, look at that 5th group. Look at the design effect for that 5th group. It's 0.65. So for that 5th subpopulation, the NHANES killed it with this sample design. You got a 35% more efficient estimate than simple random sampling for that particular subpopulation. And that's what the NHANES was designed for, is producing these domain estimates. Not the full sample estimates, the domain estimates. It did a great job for that race ethnicity group. Okay? Much better than simple random sampling. Okay? So I could do the same kind of thing for different genders, just by using over with RAA gender. Okay, there it doesn't look like there's as much of a difference. The confidence intervals are slightly separated from each other in terms of that, but we can look at that more formally, like we talked about by looking at functions. Then we can do the same analysis separately for each of the 4 age groups. Again, all unconditionally. Okay. Now we start to see some differences. Okay, now it looks like if you look at that mean systolic blood pressure, it's continuously increasing all the way out until you're in the oldest age group. Okay, and there's not a whole lot of overlap in terms of these intervals. Okay, so we can combine in Stata the subpop and the over unconditional options for the purpose of descriptive estimation. Subpop kind of defines our larger overall population, and then the over option tells us to repeat the analysis unconditionally for different groups within that larger overall subpopulation. Okay. Questions about this block of code here? Yep.
So we are having through the logic transfer?
No, these are means, remember. We're not talking about proportions here. These are not proportions. What we're trying to estimate is the mean systolic blood pressure. So everything we talked about for the logit transform is for proportions. Yeah, these are means. Yep. Other questions about this block of examples? Yep, yeah. No, see, that's the key thing. So suppose I want to look at like race ethnicity and I want to do my descriptive analysis using race ethnicity. If I did something like this, mean, and then like rid reth 1, which is numeric, but it's a race ethnicity indicator over HCAT 4. Okay. I get means. I don't get an error message. Looks like a descriptive analysis. Okay. Who in this room can tell me what it means to have an average race of 3.11? Anybody want to take a shot? Right, it's nonsense. Okay, so Stata is not going to warn you if you have a categorical variable that's coded as numeric, which is perfectly fine, and you're trying to use mean. It's still just going to compute the mean robotically. It's on you as an analyst to make sure that you've correctly recognized which of your variables are categorical and which are continuous. Okay, a lot of people will just plug in a variable like race ethnicity into a big correlation matrix, or toss race ethnicity into a regression model as a control variable, just leaving it like this. Just not the way to operate. Okay? Survey mean is not for categorical variables, it's for continuous variables. And in some cases, binary variables, and that's it. Okay. Now, I'm going to rerun this analysis because I want to demonstrate LINCOM. So I'm going to rerun the analysis where we looked at the mean systolic blood pressure for different age categories. All right, so I'm just bringing that analysis back up. The reason I did this is because every time that you run an analysis like this, Stata saves the estimates, the variances, and their covariances in working memory from the most recent analysis. So I didn't want to look at that race ethnicity example. I want to look at this systolic blood pressure example. So right now, in working memory, are saved all of these estimates and their variances and covariances, okay? Even though you don't see it exactly for the variances and covariances, right? So given that I've run that analysis as my immediate recent command, I can then use LINCOM as a post-estimation command to refer to those estimates that are saved in memory, right? So this first LINCOM line, I'm saying, look at the mean systolic blood pressure for this continuous variable that, remember, is the C dot, or we're at category 1 of age cat 4. Okay, extract that mean and its variance. Okay, and then the linear combination is simply defined as subtracting the mean for category 2 of age cat 4, which is saved in memory. So extract that mean and that variance and get the covariance of those two estimates at the same time, because we need that for the linear combination. Okay, so Stata is doing all that work for you in the background. Okay? And this is giving us our t-test for this specific pairwise comparison out of all the possible pairwise comparisons of the age groups that we're looking at here. All right, so I run this LINCOM command, and I get that difference, the estimated difference between category 1 and category 2 is about 4.01 points. And you can see that's exactly this difference in the point estimates. Okay, so that estimated linear combination is 4.01, right? The standard error of that linear combination based on the variance plus the variance minus twice the covariance of those estimates is 0.48 roughly, and all that's accounting for the design features. And the 95% confidence interval for that difference clearly does not include 0. And when I add or subtract that critical t-value times the standard error. All right, so I have clear evidence that groups 1 and 2 in terms of age categories have significantly different mean systolic blood pressures in this population. So I can reject a null hypothesis that those two groups have the same mean on that particular variable, fully adjusting for all the design features. And I could do that for all the possible pairwise comparisons of those groups. You see 1 versus 3, 1 versus 4, 2 versus 3, 2 versus 4, 3 versus 4. Like you would in an analysis of variance or something. What you don't see for this kind of approach in design-based analysis is a correction for multiple comparisons, right? We're not seeing like a Tukey HSD correction, right? We're not seeing a Bone-Ferroni correction. That stuff all has to be done manually. If you're doing these kinds of pairwise comparisons, there's no way to have that built in, these kinds of linear combinations, because this is a general purpose tool for looking at these differences. So if I wanted to implement my own Bone-Ferroni correction, for example, I could divide 0.05 by 6, because I'm doing 6 pairwise comparisons, just as an example. And I would have to meet significance at that new adjusted p-value based on all these pairwise comparisons. And there are other ways to implement other types of adjustments like that. But I can run all of these lincoms all at once, and then just kind of cycle through my output to look to see where there were significant pairwise differences. Okay. So that's setting up all those individual contrasts of the individual means set up by looking at age categories separately. Okay, questions about that approach? Any questions about what we just did here? So basically what we just did is an ANOVA without the F-test. Next week, we're going to see where to get that F-test in a regression setting. Okay? And then we can supplement that F-test with these pairwise comparisons. Okay, so that's subpopulations and linear combinations. Let's now turn to percentile estimation. So remember, Stata does not have a built-in SVY percentile. Okay, so if you look at help underscore PC tile. Okay, this is a nice command that can be used to create percentiles within a data set and display percentiles as part of the output. And you can actually turn on a weight when calculating these percentiles. So you see there's a weight option for each of these different PC tile commands. So you can get weighted point estimates using that ungrouped idea for each of these particular, for each variable that you're analyzing. But PC tile does not give you standard errors. So if you want to make inference about the percentiles or express the sampling variance of the percentiles, you're not going to get that out of PC tile. Okay, so while this is there, we can't get standard errors for these kinds of estimates. Okay, so for example, if I just said, let's see, back to that window here. Actually, we'll look at the percentile options. Right, so it's P and then the actual numbers. So if I want to get percentiles of PC tile, let's say of that same systolic blood pressure variable, BPX-SY1, I can in square brackets turn on my weight on the fly for this kind of analysis and say weight MEC 2 year. And then the options were specified as P and then integers divided by commas. So I can say like P, let's just say I want the first quartile, the median, and the third quartile, like this. Okay. Now, see, I don't even see anything to begin with. If I look at the data set here, oops, I don't see anything there either. Really what this command does is it generates percentiles kind of in working memory, and then you have to add this return list to see what they are, right? So it's like a sequence of 2 commands. So it's just not a command that's designed for descriptive inference. It's designed really for data management more than anything else. But if I see return list here, after running that command, there I see my weighted estimates. Right, and it's not even clear from that output what I'm looking at. It says scalars, and then it says RR1, et cetera, right? These are the 3 percentiles that I wanted to estimate, but it's not at all clear exactly what I'm getting here from this 2-step process. And I certainly don't see standard errors, right? So while you can get to the point estimates, this is certainly not ideal, okay? And that's why, again, my colleague Stas Kolonikov wrote this EPC tile command that we have here within the lab notes. Now, this is a user written command. Okay, so it's not part of base data. So if I type help EPC tile, okay, it says I couldn't find anything for that particular command, right? But I did find these links that help you to install the user written command. Okay, so I'm just going to click on one of those links here. And then when you click on one of those links, see how it says click here to install? That's going to install the user written command, assuming that you have writing permissions on where your Stata is installed. That's going to install the user written command so that you can now use it as a part of your current Stata session. All right. So I'm going to say click here to install. It's going to check to see that it's not already installed, and then it just installs the ado file that contains EPC tile and tells you that the installation is complete. When that's done, now I can look at help EPC tile, and now I see it like it's a regular Stata command. I see all the options, I see all the help features, etc. All right, everybody with me on this process? So this is the first time that we've looked at a user written command like you always look at in R. But this is an example of a user of Stata writing this command on their own. Okay. So now I have EPC tile available in my current session, and here's how it works. Okay. So the first variable listed is the continuous variable that we wish to see percentiles for. Then after a comma, you indicate the percentiles that you want to see in parentheses. So 10, 25, 50, 75, not separated by commas in this particular syntax. Then my subpop. Okay. So I also have to correctly do unconditional analyses in this case. I want to focus on adults only. So I specify that subpop on the fly in this case, if age 18 P is equal to 1. Then I add that SVY option to make sure that all the design features that were survey set are being accounted for in that estimation and in calculation of the standard errors. Okay. So it doesn't look like the typical SVY command within Stata. Why? Because it's a user written command. Stas could have written this however he wanted to. This is how he chose to write it. This is how he chose to make it work. We have to add the SVY option, and we have the subpop option. Okay. So I'm making sure I'm doing everything I should be doing in a regular design-based analysis, but in this case, focusing on percentiles. All right. So I'm going to go ahead and run this command. All right. Now, not super exciting in terms of the output. All right. You can see estimated coefficients without any decimal places. Okay. There's a lot of rounding going on here. You see linearized standard errors that are 0.5 in each case. Okay, it's really an estimate based on the linearization approach. You see clear evidence that these are all different from 0. I don't know why Stas is including that, but it's essentially a test of whether that percentile is greater than 0, given its standard error. But then you see these 95% confidence intervals given those standard errors for the percentiles. So that way you can make some inference, and we see pretty precise estimates of these percentiles, at least using linearization in this particular case. Okay. Now remember, BRR is better from a theoretical perspective for variance estimation, but it's off the table given the NHANES sampling error calculation model. So we can't just on the fly say that we're going to use balanced repeated replication for the variance estimation. All right, let's just see what happens if I try jackknife. Remember, the jackknife is not great either for variance estimates of quantiles. It's inconsistent as a variance estimator. It doesn't converge to the true variance. If I go back to my survey set, and then I say, as a part of survey set, VCE jackknife. So I'm saying, yes, I have these sampling error codes. I could use linearization, but I want to set the default variance estimation approach as jackknife. So I'm telling Stata to create jackknife replicate weights every time it does an analysis. Okay. I reset my survey set, and then I rerun EPC tile with those new survey features. Okay. It takes a second. Why does it take a second? Because it's running jackknife replicates. That's what we asked for. Look at the standard errors. Make a difference. Okay. For these particular percentiles, it flat out didn't make a difference. Okay. So you could change variance estimation techniques on the fly if the sampling error calculation model allows for it for certain kinds of variance estimation techniques. This is the jackknife. We can't use balanced repeated replication in this case. All right. But EPC tile will take whatever you have specified in survey set, whether it's replicate weights or sampling error codes or whatever the case may be, EPC tile will take that with the SVY option added and make sure that you're getting those design-based estimates. Here, there's no notable difference between the linearized and the jackknife variance estimates. Everybody with me on this? Yep, no?
First of all, is that why do we have to specify?
I think you can also do that. Let me just see real quick. I think it works the same way as same result. Yeah. Yeah. So you could do it either way in this case. I just wasn't sure off the top of my head if Stas's command actually would just take the dummy variable. And if you're saying it does, it does. That's fine. Yep. Other questions about this example? Okay, so just remember, if you're a Stata user and you need to estimate percentiles, you have to work through this EPC tile user written command as of right now. Hopefully, I was really hoping that with version 18 of Stata, this would no longer be an issue, but for whatever reason, they continue not to provide an SVY quantile. I have no answers for that. So in the meantime, we have to use EPC tiles.
That command in term isn't, you don't need to go for it because I ran this code, but it's giving me an error. It's saying that it's not recognized. I don't know.
It's saying what?
Unrecognized.
Did you install it like I showed before? You have to install it. I went through that process of installing it first of all. Yeah. So what you would do, George, is this here. You'd say find it at EPC tile or help, either way. And that's going to bring up online links where you can download the software for those user written commands. I clicked on one of those links, and when you do that, you have this option that says click here to install, right? It's not a base command. It's a user written command. Okay, other questions about this example? Okay, let's move on. Cross tabulation, okay? So now we're gonna look at those Rouse-Scott analyses for dealing with categorical data, looking at associations of various sociodemographic characteristics with having an irregular heartbeat in the NHANES. So this is a relatively rare condition. And we want to see if different sociodemographic subgroups are at more or lower risk, higher or lower risk of having an irregular heartbeat based on the NHANES data collection. Okay. So creating a couple dummy variables first, and this is more evidence of what you might do in advance of an analysis to create your different subgroups of interest, your subpopulations, right? First one, I'm creating an indicator variable for the youngest age group, females. That might be the subpopulation I'm interested in, right? I'm interested, let's go revisit what my youngest age group is. Females between the ages of 0 and 30. Okay, that might be the focus of my whole research, right? If I want to do an unconditional subpopulation analysis for that subgroup, this is the sequence of commands I might use, assuming that there's no missing data. But see, even if you have missing data, they get lumped into a 0 in this case. So everybody gets a 0 on that to begin with. And then for people who have gender equal to 2 and age cap 4 equal to 1, they get a 1. That's my binary subpop indicator that I can use for subsequent analysis. Okay, so I can run that sequence of commands. Now I have that subpop indicator in my data set. I can use it whenever I want to. Okay. Same thing here for question. I will, yeah. I'll before I do these analyses. I'm just doing the data management right now. Yep. Okay, next one. I'm saying I want age category 4, so I want the oldest, and I want African Americans. Again, that could be the focus of my whole research. I'm concentrating my estimation on elderly African Americans. This is the kind of subpop command that or subpop definition that you would use before you do the analysis. Right, so I'm going to create this particular indicator as well. So now I have both of those subpop indicators in my data set. I can work with them whenever I want. I haven't deleted any cases. I'm still working with the entire NHANES data set, but I just have these subpop indicators available for my use if I want to do those subpop analyses. Let's look at how much sample we have in each of those subpopulations, these two tab commands back to back. Okay, so I have 2,619 respondents who are young females. And I only have 157 respondents who are elderly African Americans. Okay, that's the kind of size of a subpopulation that's going to cause a lot of problems when I do conditional subpop analysis, right? We're going to see that in a second here. If I was to delete cases that were not elderly African Americans, I'm going to be deleting a lot of clusters from that analysis, okay, for linearization. All right, so I have these two subpop indicators. Let's look at a couple different analyses focused on those subpopulations where we're testing associations of interest. Okay, so let's think about the qualitative research question that we're answering in each of these cases. Okay, so first command here, my subpop is young females. All right, that's the subpopulation I want to focus on. And I'm looking at the association between having an irregular heartbeat and marital status. So I'm saying among young females, is there evidence of an association between marital status and having an irregular heartbeat? That's my research question. Okay. Second tab command, I'm saying among elderly African Americans, is there an association between education status and having an irregular heartbeat? Okay. Two different research questions that we're trying to address with these design adjusted cross tabulation analyses. Okay. Now, this is one way to do it. I'm illustrating the column proportion approach to interpreting this kind of analysis. Another way you could do this is to say SBY subpop age 1 fem. And remember, in tab, the first variable listed is the row variable. So if you like thinking from left to right and thinking predictor, outcome, the way you look at these crosstabs, you can write it as Meerkat first, irregular second, and then ask for row percentages for the standard error. Okay. Everybody see the distinction there? If I put what we think of as the outcome first, and I want to think about differences between groups defined by the predictor in terms of proportion on the outcome, I have to ask for column percentages, the way that these tables are set up. If I put the predictor first, defining the rows, I have to ask for row percentages. Okay, I get the same estimates either way, but just depends on how you think about a contingency table like this. Okay. And again, I'm doing this unconditionally for young females. Now notice, there's no chi-square option. Again, by default, Stata is automatically going to give you that most powerful Rao-Scott test in the output. There are other options that you can specify, but the default choice is that Rao-Scott test. Right? So I'm going to run this command. Okay, let's see what we have here. Among these younger females, okay, what are we seeing in this crosstab? Okay, what's the issue that we're seeing here?
There's no any categories. Any combination.
Well, so let's look at row 2, for example. So row 2 is people who were previously married. Okay, what is that telling us about individuals who were previously married and whether or not they've had an irregular heartbeat?
There's no cases those.
Yeah, so our estimate would be that there's not a single person in the population who has either been previously married or never married who has an irregular heartbeat. Everybody who has an irregular heartbeat is married. Those of you who are married will be nodding your head saying, sounds right. Okay, but that's what this estimate is saying. Okay, so we have to think about, what are we going to do in that particular situation? We get the Rao-Scott test automatically, but it's based on a table where there's no variability in 2 out of the 3 groups. Okay, so we might want to say something about this qualitatively because we're estimating that the prevalence is 0 in 2 of these groups. Okay, that Rao-Scott test, I think as Jupiter was saying to begin with, you see that uncorrected chi-square based on the weighted proportions. That's the first thing that's output. Then it jumps right to this design-based F statistic with 2 decimal degrees of freedom values. Again, that's because of the second order correction. That's what you should be reporting, are those actual decimal values. Don't round them, report them as they are. Those degrees of freedom can be non-integer. Then you see the F statistic, fully adjusting for the design features, and the corresponding p-value. So that p-value would suggest that there's no evidence of an association between these three, of an association between marital status and an irregular heartbeat among young females. That's our subpopulation, okay? So you get that test automatically. It's just that in this case, right, there's some concern in that we don't really have any estimation in two of those three groups. Okay, so it seems like it's exceedingly rare in those particular groups. All right, I forgot to fix the linearization. So let me go back and do that. So it's still using the jackknife. That's why it took a second. I'm going to go back and reset this to be my survey set. All right, so now the variance estimation method is linearized again. I'm going to rerun that last command. Here. It's not going to change anything about my estimation, okay? But I still see that issue with the zeros, right? Okay, now I just have the linearized standard errors instead of the jackknife standard errors. And if you look at those in the first row, again, they're identical. Okay, okay, now let's see what happens when we go to our elderly African Americans and look at the relationship of education with having an irregular heartbeat. Now let's just look at the column percentages as a contrast. Again, I'm using subpop here. Now, see, I have to look down in each of the columns to see the proportions with an irregular heartbeat. So among those with the lowest education, I see about 8% are estimated to have an irregular heartbeat. It's pretty high. Okay. Next lowest education, high school, 5.8% estimated, huge standard error. Right, these are pretty unreliable estimates because the standard errors are almost as big as the estimates themselves in this case, but to be expected with such a small subpopulation. Okay. Group 3, 14% estimated to have an irregular heartbeat, those with less than college education. And then for those with college education, none are estimated to have an irregular heartbeat. Okay. So what do we make of that? Well, it's not very clear because again, pretty small sample size, but these are pretty unreliable estimates. So, but that's what we're seeing in this particular case. I want to point out this at the bottom. Okay. When we looked at this particular subpopulation, Stata found an entire stratum that had no elderly African American males, or just African Americans in this case, no elderly African Americans. So Stata's decision was to entirely drop that stratum from all the calculations. What that means is that we now have 29 PSUs and 13 strata, which means 16 degrees of freedom. Not going to make for a huge difference. Remember, the full design had 31 clusters and 31 clusters and 14 strata. So 17 degrees of freedom. Stata temporarily removed that particular stratum from the calculations here. So our confidence intervals are based on only 16 degrees of freedom in this particular case, as opposed to 17. So that's how Stata operates. Stata will drop those particular strata that have no sample present. Okay? Based on that Rouse-Scott test, which is printed automatically, again, no evidence of an association. Seems like a pretty common estimate across these subgroups, but again, pretty unreliable estimates in this case, given the small sample size. Looking at those standard errors.
Okay. Yeah. How do you find how do you think it's greater than something or greater than something?
So that's a good question. Who can interpret that p-value? What decision do we make? What's our null hypothesis and what decision do we make? Who can walk me through that? Question, you want to just say, what's our null hypothesis?
Independence.
The null hypothesis is that these two variables are independent. So based on that p-value, do we reject that null hypothesis or do we fail to reject that null hypothesis? Fail to reject, right? We would reject it if that p-value was below some arbitrary value, 0.05, 0.01. That's evidence against that null hypothesis. This is zero evidence against that null hypothesis. Okay, other questions about those two crosstab examples? Any other questions about those two crosstab examples? Okay, so everybody's comfortable with crosstabs, those of you who are Stata users, that is? Very comfortable? Okay. Last couple things here and we'll take a break. Here is the conditional approach to what we just did. Okay. Notice what I'm doing. I'm saying SVY tab. I have my row variable, I have my column variable, but instead of using subpop, I'm saying if. And I'm saying if my subpopulation indicator is equal to 1, right? If I try to run this analysis, look what happens. No standard errors, no Rouse-Scott F-test. All I see are my point estimates. Okay. And again, this is not Stata breaking. This is you breaking. Right? Because of that conditional versus unconditional issue. We're focusing on a very narrow subpopulation. And if I look at my survey describe, if age for underscore black is equal to 1, there's 3 different strata that now only have a single sampling area computation unit. And if I'm using linearization, it's a non-starter. That's Stata's default for that single unit option, survey set, is to have missing values for standard errors when there are strata with only a single cluster present. Okay, this is why we're not seeing a Rouse-Scott F-test and why we're not seeing standard errors. Okay, alternative, okay, I could use jackknife. Run this last command. I could say SVY VCE jackknife. I'm not saying to do this, I'm just driving home a point. You never want to use if, I'm just making a point here. If I change the variance estimation to jackknife, still, right? It's saying you're giving me a sampling error calculation model that has that has strata with only a single cluster present. It doesn't even help that. Okay. So, Stata users, if you see this, it's usually not going to be the data producer. It's something that you've done conditionally that causes this kind of problem. Okay. Okay, last point, also just to illustrate estimation of totals. If we want to estimate the total that have ever had an irregular heartbeat, quite simple, just use the total command as opposed to tab. That'll sum up everybody with a 1 or a 0 on that particular variable, right? So you see there's an estimated total of, among adults, about 36,700,000 people who have an irregular heartbeat. So while it's rare, it's definitely not trivial. There's plenty of people who could have health issues related to this problem based on this estimated total. Okay. So pretty easy to generate totals. Just remember, we don't want to do that with normalized weights, right? The NHANES uses population scale weights. We want to make sure that we have population scale weights before estimating these totals. Okay. And then if you're done with this particular Stata session, just run this command that says log close, and that will timestamp your external log. And then you can open that up, look at it, go back and review your results, etc. Okay. Questions, comments, thoughts on the Stata examples? Any questions or comments? Yep, he's right.
For the PDF from the new file, please.
Yep.
The line that related is this word. When we make tab irregular.
This one up here?
FH, no, the F condition. The one that before making the jackknife.
This one?
Down, yes, this one. Before making jackknife, it doesn't give us any results. But when I make sub-bob for among those age 4 underscore black, I have a good result.
Right. That's the difference between unconditional and conditional. What I've done here is conditional, and that's why we're having the problem. Because we're physically deleting cases that are not in my elderly African-American category. That's what's causing the problem. When you use subpop, you're processing the entire data set. You're not deleting any cases. You're processing the entire data set, all those clusters that have sampling zeros, they're being recognized for variance estimation. Here, those clusters are being deleted. And when Stata sees that there are some strata that only have one cluster, it can't estimate variance from that stratum. That's why it's not giving you anything. Okay, any other questions about these examples? Okay, let's take a break. It's about 11:13. So let's break until about 11:20, and then we'll go through the R examples and see how to do all this within R. Okay. Okay, so I'll start back up at 11:20.
You guys are very that like
You're using a very, very, very obsolete version of Stata. That's the problem. Okay. So that syntax is for version 17 and above. You wouldn't actually get support for 15 right now. Like if you had a technical problem, they would say, sorry, we're not supporting it. Yeah, that's the issue. So in this one, I'm trying to remember how that was specified. I think it's like,
Princess Diana. Yeah. It's really nasty. That was a very good joke. Yeah, perfect build up. You need to check every day.
yeah, I don't remember off the top of my head. It was something, it was just a different syntax. So like, it might be if you look at help.
Okay, now results or homework. Results in
Oh yeah, that's what it was. It was continuous variable in brackets and then the value of the categorical variable right after. So it was.
You're right.
Oh, right.
90%.
So the
I know the answer to what you
this is a different syntax, but yeah, 15 is just kind of
ready to decide.
Just 1 second, just loading that R code up here.
This one part is
Okay.
So, select here. So the format is here. So what I said,
Well, this says your subpop is everybody. So.
Yeah. So I'm just curious about that subpopulation between the mind.
Show me how you form subpop.
This was case. Yeah, this was like
I used
yeah.
like the words of
Okay, you're not replacing it with a zero. So you're forming this sub up indicator to be whether or not FS17 is electrolytic. So yeah, drop the sub up real quick and then just run that gen line. Don't run the replace line.
Something as we separate a.
And then just look at a tab on sub up.
I use the boomer one. But for the cache thing.
So there's your indicator.
Yeah. So it should be like in this form. So when I use this in like here, if I use this,
It's like
so like having the similar one that I was previously having, like number of observation previous sound.
That's right.
Yeah. So is this the same?
That's all right.
It's all right. Yep. So one thing I'm just having trouble is all the values like charge over indicator traffic is matching with the report, even the standard error is matching with the report, even these two. The standard error, like sorry, def is exactly matches with the.
There's different ways to calculate def. So Stata is using one particular way of calculating def, but there's a number of different formulas that might be used depending on the software. So this is just one possible, plausible way to calculate def. Like some people calculate def, for example, using the unweighted estimate in the denominator instead of using the weighted estimate. So like that's
Maybe, yeah, that's right. Because in the report they used spices for the calculation of design effect. Maybe
there's probably an issue there.
Issues between.
But just you can, if you dig into the Stata documentation, like you'll see exactly what formula they're using, and you can just report that that's what's being used.
So now I'm going to use this set as some.
Yeah, that looks right to me.
Yeah.
I just finished writing this email.
Where are here? Here. Here. Here.
I don't know, there's a way to see. Yeah, but I don't think. But that means the way it's solved.
I have a quick question on my end. So we only want to do there again, 2016 with the education attitudes model. So they follow that follow your micro two cohorts. I looked into it, but I haven't figured out which side.
So you're saying the 2015 respondents have their own replicate weights,
Yes.
and then the 2011 respondents
No,
have.
they don't have the replicate weight for the 2016. They only have the final analytic weight for the round 2016.
Okay.
But they provide the replicate weights for the 2011.
Okay, so are the 2015 saved in one set of variables, and then the 2011 are saved in a different set of variables, like for the replicates?
Yes.
That's
Good
okay.
for us.
Because then there's no apparent way to line up those replicate weights with each other because they're not necessarily always referring to the same replicates.
But is it because of the longitudinal nature of it that we can actually use it?
If the 2011 people were also in 2015.
They are. It's just the reason why they replenished the cohort. Some people died.
Yeah, that's a challenging issue. Because you can't stack those replicate weight values with each other because they're just different. It's just different information depending on the code. I think what I would do in that case, again, just for the purpose of this kind of illustration, is use whatever respondents were available in 2011, 2015, and 2016. So in other words, don't use the new replenished sample from 2015 that was given a unique set of replicate weights. just use all the respondents that were there for all three, and then use the 2011 replicate weights for that group of respondents. I don't know the immediate answer for what to do about the different set of replicate weights that was added for the 2015 refresher samples. That's a really unique problem.
Okay, so,
So I would just set them aside. You could treat them like a sub-pop. Or just leave them out of the data set. I don't know. It's a tricky issue. Like, I'd probably just leave them out of the data set and say that the 2011, whoever was sampled in 2011, like, that's from the population you were interested in. And then you followed them over time. And you're going to use whatever replicate weights they had available from 2011 with their 2016 weight that was computed for them, and just set aside the refreshment sample. I think that's the way it's going.
so I guess the first step for me is to look into whoever responded to the model that I'm interested in and see how much it.
Right, just, but just leaving aside the refreshment sample in 2015.
Okay.
So just focus only on people who were there in 2011 and then in theory could have been there in 2015.
What is the size?
That's part of the problem. Right? I mean, you could try to bring in the refreshment sample, but you need some way of estimating variance. And if they have a different set of replicate weights than everybody else, I got to believe though that there's some kind of guidance that's been provided for how to combine those replicate weights. And I can ask people here, like what to do in that situation. But yeah, it's a tricky problem.
I haven't read the documentation for 2011.
Yeah. Yeah. So it's we got to figure out something to do with those. I think that what I suggest is the best way to do that. Okay. Yep.
Yeah. Yeah.
Okay, let's start back up again. I have copied the R code into RStudio. So I have this in an R script window here. And we're just going to walk through kind of the replication of what we just did in Stata using the R functions as an alternative. Okay. So first things first, we have to load the packages that are needed to execute all these different functions. So I'm loading the tidyverse, the family of functions in the tidyverse. I'm loading the survey package, okay, which has all of our key analysis functions, and then also Haven for some key data management functions. All right. Same thing we looked at last week. I'm going to read in the Stata version of the data set using read DTA. Okay. And then I will change all those variable names to lowercase, and then look at a frequency table for the age variable here to start with. Okay. This assumes that we have the working directly correctly specified. I do not have that here, so let me get that real quick. Sorry, I thought that it's saved from my previous session. So set the working directory to be. You guys can do this on your own machines as well if you're following along. Okay, let's try this again after I set that working directory. Now you see the frequency table on age, and we have the NHANES data set read into this object called NHANES. Okay. Okay, now we're going to look at that code to create the 4-category version of age cat4. And again, we're using a piping operator with mutate, okay, to create those 4 different categories using a series of if-else functions to mimic what was being done with gen and replace within Stata. And you can see it's the same sequence of conditions to set the values on that new HCAT4 variable equal to 1, 2, 3, or 4. All right, so just different code here to do that particular recode. And I'm going to add that field to the NHANES object. So I now have HCAT4 as a part of the NHANES object. Okay, so I can look at the table, showing missing values if they exist of that HCAT4 object. And again, there's no evidence of any missing values. So I have 0 NA values, which is a good thing. All right, now I'm just going to look at a simple frequency table on that sub-pop indicator that's already been created here. Okay, so same thing like we saw in Stata, I see the number of adults, the number of children, and then no missing values on that sub-pop indicator. I'm going to declare all of these categorical variables to be factors within R. So remember, we need to do that first to make sure that the categorical variables are treated correctly in all of the R analysis functions, and they're not treated like numeric variables. Okay. Another cool thing that's being shown here is how, as a part of mutate, you can add labels to each of the categorical values. So we showed how to do that within Stata. Here's how you could do that within mutate within the Haven kind of series of functions. You can look at that labels argument as an option in the factor function. Okay? So normally we've just said factor and then the name of that variable, but you can be explicit and add that labels argument to apply a unique label to each of those values. That way you're going to see those labels in all the output. You're looking through these analyses. So I'm doing that for each of the different variables, and that's just a general argument to the factor function when you're defining these new factor variables. Okay. All right, so I'm doing that for everything, including irregular, which is already a 1, 0 variable, so I don't need the labels there. Okay, and again, I'm creating these new versions of each of these categorical variables by overwriting what was in the original NHANES data frame object with this series of functions here. So that's a really handy recoding and labeling sequence of commands that you can use within mutate. All right, so now all those variables have those strings. So if I look at view NHANES to take a look at the actual data, you'll see that in the output, or in the table rather, you see the labels of these factors rather than numeric values. So some people prefer that as a way of looking at the data. Okay. Okay. Close this. All right, now also we can add these interactions between age and sex if we want by using that colon operator. So that creates a new variable that combines categories of age, cat, and gender all into one new variable. Again, using mutate if we wanted to do that for any purpose. Okay, once we have all the variables, we've declared our factors, etc., in the NHANES data frame object. Now we're going to create that design object. And one of the inputs to that design object argument is going to be that NHANES data set that we've been forming. Okay, so as a reminder, we have our stratum codes with the variable after a tilde, the cluster codes after ID, the weights after a tilde, the name of the data frame object, and then declaring the clusters to be nested within the strata. And that's how we set up that design object. And I'm calling that NHANES underscore SVY. You can call it whatever you want it to. All right, so now I have that NHANES SVY design object, and I can look at a summary like we did with SVY describe. Again, you see a basic summary of the sample design that was specified, the distributions of the probabilities that were the inverts of the weights, distribution of the sampling area computation units across the 14 different strata, and then the variables contained within the data frame object. So always a good practice just to check that and make sure you're not missing anything with the way that you've set up the design features. Okay, so we have NHANES SVY ready to go. Now, one way, remember, to do the unconditional subpopulation analysis within R is to use this subset function. So when the subset function is applied to a design object that's already been created, it will apply the unconditional idea to that particular design object. So still the same essential design information, just with that 1, 0 indicator essentially added to distinguish between your subpopulation and everybody else. So I'm creating a new version of the NHANES survey object that focuses on that specific subpopulation using this subsetting function. And again, this is especially important for linearization, not for the replication techniques. Okay, that's one way to do it. I could have also done SVY by. I prefer this way because this is basically the analog of using subpop with an indicator variable within Stata. So I like to have this new design object available for my specific subpopulation purposes. Okay. So once I have this unconditional subpopulation version of the design object available via the subset function, I can then input that subpopulation design object into all of my subsequent analysis commands. Okay, so now in all these commands I'm using here, I'm inputting sub NHANES SVY instead of the original NHANES SVY to implement the unconditional approach. All right, so first of all, I can look at the overall mean systolic blood pressure for the adult population and its linearized standard error. And then if I want a confidence interval again, I just wrap that within the confident function. And that gives me the 95% confidence interval based on the linearized standard error for the overall population mean. Okay. If I want to break that subpopulation down by different subgroups defined by race, ethnicity, or gender, or age cap, I can use SVY by. So, right, this is the R analog of what we were doing with subpop and over within Stata. Okay, R's analog is using that subset design object with SVY by to do that analogous analysis. All right, so I'm looking at the mean systolic blood pressure by race ethnicity for the adult subpopulation, removing missing values, and using the mean function to do that. Okay, is everybody following what I'm doing? I want to make sure everybody, especially those of you using R, I want to make sure that you're following. Okay, okay, so when I run this SVY by, I'm going to get my 5 point estimates, my 5 weighted point estimates, and then the 5 linearized standard errors, which again are going to match what we saw within Stata. And if I want my confidence intervals for each of those means, I again just wrap that same set of results in the confident function. And then I get my 95% confidence intervals for each of those means. You can do the same thing for gender. I'm just going to run these 2 commands combined. Okay, so I get my weighted point estimates separately for gender, and then again, those 95% confidence intervals, which don't exactly overlap in this particular case. All right. And another approach to doing this in general, remember, you can save the results of a survey analysis in a new object and then work with that new object if you don't want to keep writing that function over and over again. So what I'm doing here is I'm saving the results of the age cat 4 analysis in a new object called BPAge, and then applying subsequent commands or functions to that new object, as opposed to just writing the same function over and over again like I did above. So this is another way to go about doing that, and this would give me the estimates and 95% confidence intervals for HCAT4. Okay, so that's just a matter of personal preference with how you want to write the code. Now, remember, like we talked about in lecture, to get the subsequent comparisons of means, okay, between different groups, like we said, the survey kind of t-test approach, we do have to start with that object containing all the results and then apply SVY contrast to that new object. Okay? And then we create a list with all of the new linear combinations that we want to form. In this case, I'm creating a linear combination called diff, which is taking the difference between groups 1 and -1. Okay, or I'm sorry, the difference between groups 1 and 2, and that's set up by using coefficients of 1 and -1 for those 2 groups. Okay, and groups 3 and 4 aren't even being considered. All right, so I need that object contain the results of survey by, and then I create that linear combination as part of a list, indicating what the coefficients are that define my linear combination. All right, so this is a little bit more long-winded than the way that Stata does it. But this is how you would set up that same kind of survey contrast you're using R. All right, so I'm going to go ahead and run this. Now, notice this interesting warning message that R prints when you're using SVY contrast. By default, when R is using linearization, it's not calculating the linearized covariances of those different estimates, okay, when you do the SVY by analysis. By default, it's going through and it's calculating each of the variances of the estimates. But unlike Stata, it's not calculating the covariances of the estimates. And remember, like we talked about on Wednesday, when you're calculating the variance of a linear combination, those covariances become very important. I was doing this for like a computational efficiency thing when using linearization. So we need to think about a workaround when doing these contrasts. If you want to look at those covariances and again, compare standard errors when those covariances are taken into account, you have to use a replication technique to calculate those covariances within R. Fortunately, there's an easy way to do that on the fly like we've discussed by using as.svrepdesign. Okay, so in these subgroup analyses, again, you're only going to get these covariances by using a replication variance estimation method, right? So in this case here, the default is to use JKN, okay, the jackknife repeated replication approach. So this line says, create a new design version of the original subpopulation object, but now including replicate weights, jackknife replicate weights, to be used for variance estimation purposes. So we're kind of like, you know, going down the inception ladder here. So we started with the main design object, subpopulation object, now the subpopulation object with replicate weights for the purpose of computing these covariances. Okay, this is something unique to the way that the survey functions are operating. Right, we're going to see how it compares the covariance version to the non-covariance version. Right, so now that I have this new subpop jackknife replicate weight design object, I'm going to input that to SVY by to do the same analysis. I'm creating a new object called bph.jk for the jackknife version of that. Okay, so I'll go ahead and run all of these here. All right, so now I have my new object bph.jk. I can look at the estimates and the confidence intervals, and by using that combination of print and confident. So those are now jackknife standard errors, okay, using the jackknife idea. Now I'm going to run that same SVY contrast to the new object containing the jackknife standard errors and covariances. That's the difference here. Same contrast that I requested initially called diff. Now when I go ahead and run this, no warning message. Okay. Now the variance of that linear combination is accounting for those covariances, which were computed using the replicate weights. Let's just compare the standard error. Here, when accounting for the covariances, it was 0.48. Okay. Up here, when ignoring them, it was 0.78. It's a big difference. Okay. So this is something very unique again to R, the fact that when you're using linearization by default and you're doing this subgroup analysis using survey by, those covariances do not get saved in memory. We need to look at the replication versions of those covariances. And that now gives us a much more efficient contrast because we're taking those covariances into account. Okay, everybody with me? This is something very idiosyncratic to doing this kind of analysis within R, but it also illustrates the importance of taking those covariances into account when you're looking at these linear combinations. Okay, everybody with me? Questions about this step here? Okay. All right, so that's with contrast. And again, I can set up the same kinds of contrasts using preferably the jackknife object. Here I'm using the linearization object. By changing where the 1 and the -1 appear in this list of estimates. So this is comparing group 1 to group 3. This is comparing group 1 to group 4. This is comparing group 2 to group 3, and so forth and so on. If I want to set up all these different pairwise contrasts. And if I'm using that original linearization object, every single time, I'm going to get that warning message. So R is reiterating that that covariance is not being taken into account when looking at this particular analysis. All right. Okay, so if I change all of these to .jk across the board, and I rerun these 6 commands, I get the same point estimates, more efficient standard errors, and no warning messages. Okay. Okay, so those of you using R, if you want to do t-tests and things like that, this is very, very important. Okay, to be aware of this, the need to use these replicate weights and this kind of, and you could also use BRR if possible, or bootstrapping if available to do this. Okay. Okay, let's turn then to quantiles within R. So again, in R, this is more straightforward because the R survey package already has the SVY quantile function as a program part of this, implementing what's available in the literature, okay? So if I want, like we did within Stata, the 10th percentile, the first quartile, the median, and the third quartile, okay, I use this SVY quantile function. The continuous variable name comes first after a tilde. I'm using my subpop object. I'm specifying a vector of those 4 percentiles, getting rid of missing values, and requesting confidence intervals based on this kind of linearization approach. All right, so I can run that function, and there you're going to see for each of the quantiles the point estimate, like we saw in EPC tau. Okay, the standard error, which you see EPC tau rounded that to 0.5. Right, you can see the actual linearized standard error is like 0.4739 something, but EPC tau and Stata rounded that to 0.5. Then you see the 95% confidence interval for that particular percentile based on linearization. All right, so same essential information that we're getting from EPC tau, okay, but available kind of more quickly with this built-in SVY quantile function. So truthfully, I use SVY quantile, especially when replicate weights are available, if I'm working on a project that requires estimation of percentiles. I'll just use this version of the SVY quantile. Okay? So pretty easy to do that. Again, remember that ideally we're using replicate weights, especially balanced repeated replication weights for estimation of quantiles and their standard errors. So ideally, that sub NHANES SVY would be a replicate weight object based on BRR or based on the bootstrap. Okay? Linearization is kind of the next best thing for the purpose of quantile estimation, like we talked about this week. Okay. Okay, so pretty straightforward with quantile estimation within the survey package. Here we can look at estimation of the overall proportion that have an irregular heartbeat. Remember, we declared irregular to be a factor in the earlier mutate command. So I can just declare the the irregular variable as it is here in the data frame object as a part of SVY mean, and it'll still be treated like a factor. Okay. So let's go ahead and run these, and I'll show you the difference between these two design effects here. Okay. So irregular, the proportion that we're really interested in is that irregular 1, as it's labeled here, again, because this is a factor. So that's our weighted estimate of the proportion of the adult population with an irregular heartbeat, the linearized standard error, and then the corresponding design effect. Now, the reason I distinguish between true and replace, if you're working with normalized weights, which is not the case here, so this is why the design effects are identical, but if you're working with normalized weights, okay, replace needs to be used instead of true. Otherwise, the survey package is going to argue that it can't find a population scale version of the weight to use when computing the design effects. So when calculating design effects within R wants to see a population scale weight. That def equals replace is a workaround for the case of normalized weights. Here it doesn't make a difference. But in the case of working with normalized weights, you won't get a result if you say def equals true. You'll get a result if it says def equals replace. It's a workaround for the case where you're dealing with normalized weights. I just want to illustrate these two different options in that case. Okay. Okay, so still good looking design effect in this case for that particular estimate. It's less than 1. Okay, now cross tabulation within R. Again, within R, this is a 2-step process. Okay, so remember, Stata gives you the Rao-Scott F statistic by default. Okay, within R, you actually have to request it after looking at the table. Okay, so the 2 steps. First of all, we use SVY table to get the actual crosstab of interest, whatever estimates we might be looking for. Then after getting that table, we separately run SVY chi-square to get that design adjusted Rao-Scott test. It doesn't come automatically with SVY table. All right, so let's run SVY table first, and notice the N total argument. That's going to give me total proportions in the overall table. So I'm going to go ahead and run this table for gender and irregular heartbeat. Okay? And there you can see the proportions of the overall population. Okay, that's that N total equal to 1. That's giving me total proportions in that 2x2 table that sum to 1 for the entire population. Okay, so again, I would interpret those, for example, as saying that 50.48% of the population is estimated to be females with a normal heartbeat. Okay, those aren't row or column percentages. Those are total proportions in the way that SVY table works by default. Okay. Now, once I have that table, if I want to test the null hypothesis that those 2 categorical variables are independent of each other, I would use SVY chi-square with the table set up in the exact same way. Okay, so column variable plus row variable, or you can do it the flip way around if you want. Same subpopulation object, deal with missing values, and give me the F version of the Rao-Scott test that Stata is giving us by default. Okay, the default, it's going to give you the chi-square version of that second order test. All right, so I'll run SVY chi-square. Okay, so you're not going to see fancy output because you've already looked at the table. The whole point of SVY chi-square is to compute that Rao-Scott test. Right, so you see the Rao and Scott adjustment to the standard Pearson chi-square. There's our F statistic, the degrees of freedom values, and then the corresponding p-value for that test. And for a 2x2 table, you're not yet going to see decimal degrees of freedom values, but you should still report these. You start to see decimals with more than 2 rows or more than 2 columns in the overall table. Right? So no evidence of an association between gender and having an irregular heartbeat. That would be our ultimate conclusion based on this Rao-Scott test. Okay. Okay, and if we wanted to see row proportions, say, so a breakdown by gender, by age category, by marital status of the proportions with an irregular heartbeat, you can list all those different variables separated by plus signs in SVY by. And it'll give you separate sets of output breaking down the irregular proportions for all those different factors. So in SVY by, you can have more than one grouping variable listed as that second argument. That's the example here. That's what that's showing. So this is just kind of a shortcut to get all of those subgroup analyses listed at once. Okay. So you see this kind of big picture breakdown of all these different cross classes of those different variables. So that's a nice feature to really break all this down. Then what we're doing next is looking again at those specialized subpopulations that we were interested in within Stata. Remember, we started with young females and we looked at elderly African Americans. And so we're just using subset again, but we're starting with the original NHANES survey object, not the subpopulation, because we're not just looking at people ages 18 and above. Now we're including everybody between the ages of 0 and 30, right? So we have to go back to the original design object and then apply subset to that design object to create another new design object. I just called that SVY1. Here is my condition, referring to the factor labels that we created earlier in the mutate command, right? Once I replace those values with the actual labels, I have to actually refer to those labels in these kinds of conditions within R. Okay, so that's why I'm referring to the string values here, as opposed to the numeric labels, because we overwrote those numeric values with the string values with that earlier mutate command. Right, so this creates my new subpopulation design object called SVY1. Okay, and then I can summarize it. Now, if I want to look at the relationship between irregular and Mercat for that subpopulation, I can use survey chi-square with that subpopulation design object and just jump right to that Rouse-Scott test. This is not going to give me the actual estimates. I need to use either survey by or survey table to get those. But this will give me that Rouse-Scott test for that particular subpopulation. Okay, and we see exactly what we saw with this data. And now you see again that we have those decimal degrees of freedom, because now we're dealing with more than 2 groups as one of the categorical factors, okay, for that Rouse-Scott F test. So remember that Rouse-Scott F test, we got to report both degrees of freedom values, not just one. Okay. Okay, we can do the same thing then to get the breakdowns of the row proportions. I'll just do this by Mercat so that we can match this up exactly. So I'm going to break down the Mercat proportions for the SVY1 design objects, just to match the results above. So there you see for different categories of Mercat, the estimated proportions with a regular and irregular, with a regular 1 and a regular 0. We see the same issue that we saw within Stata, right? There's only an estimate available for the married group as opposed to the other 2. So that's like what I mean by that 2-stage process. You have to look at those row proportions separately and then get the Rouse-Scott test using SVY chi-square in this particular case. Okay, same thing for the older African Americans. I'm creating that new subpopulation design object here. Then I'm running the Rouse-Scott test for that new association between irregular and education. Again, no evidence of an association. If I want to see the actual row proportions, I can just copy this SVY by command or function, and then look at edcat as my grouping variable, and SVY2 is my subpop object, and then run that. Okay. There I see those same point estimates, the proportions that we saw within Stata for that particular cross tabulation that now matches that Rouse-Scott test. Okay. Everybody with me on that kind of 2-step process with these Rouse-Scott tests in R? Any questions about this process here?
I have a question about the difference SVY table and SVY by.
Yep.
I understand that SVY table, when you put any total equal 1, you got the total proportions.
Right.
And SVY by row proportions.
We could get row or column, right? You could break this down. If you just flip like education, cat, and irregular in their roles here, you could get a column breakdown, right? This is just giving you row proportions. Yep. But that's the distinction, right? SVY table is designed to give you the total proportions in that cross classification. If you want row proportions or column proportions, you have to use SVY by.
But the argument, any total inside the SVY table, I can change this argument to get other.
Yeah, you can definitely change that, but that's the way that you would get total proportions out of SVY table. That's what a lot of people ask, where can I get those? You have to get those by setting n total to 1. You could change that argument and give you the same results as we're getting in SVY by, certainly. Yeah. But that's how you would get the total proportions. Okay, other questions about these functions? Everybody's clear on the Rouse-Scott testing idea with these cross steps, because again, you're going to get a chance on homework number 3 to carry these out. So, okay, final thing, we can estimate totals using the SVY total function within the survey package. First variable is simply the variable to be summed, then our design object, then the same arguments we've been talking about previously. So if I want to see the total of people with an irregular heartbeat, I can just run that same analysis, and you'll actually see the totals for each possible value of that factor if you've declared a variable to be a factor. So the sum of the values on 1, like we saw within Stata, it's about 3.7 million that have an irregular heartbeat. Okay, and the standard error and the corresponding design effect. Okay, so you can see there's a gigantic design effect for for the total without an irregular heartbeat, but we really don't care about that particular quantity. So a little bit of no reason to really look at that. So, okay. Questions about totals? Pretty easy to do that, Georgia.
Why is that so big?
Who can tell George why that is so big? Let's go back to our definition of def. Why is that so big? It wasn't designed for that, right? But why is the actual calculation so large? Why is it so large? For this population, right, what's that B hat in each of the different clusters? Yeah, it's the B in that calculation. It's gigantic for that particular estimate, right? Because we're basically talking about the US population of 220 million if we look at that zero count, right? Yeah. Okay, other questions? So that's pretty much everything I want to illustrate within R. So depending on whether you're using Stata or R, you should now be armed with the code to implement all the different kinds of analyses descriptive that we talked about this week. Percentiles, categorical data, cross tabulation, functions of estimates, things of that sort. So you should have what you need now to finish off the exercises in homework number 3. And again, I would encourage you to be making progress on your final projects with these kinds of descriptive analyses right now, if that's going to be a key part of your story on the final project, because next week, we're really going to be shifting gears and getting into regression modeling. Okay, so we're going to start talking about multivariable modeling as opposed to just single variable or bivariate analysis. We're going to get into multivariable analysis, looking at predictive models for different outcomes and different kinds of models that we can fit in a design-based framework. Okay, so that's going to be our primary focus starting next week with linear regression. Okay, questions, comments, thoughts? Everybody in good shape?
Brady, this is Brian.
Yeah.
I'm having an issue with the lincomp command in Stata. It says the variable HCat not found.
Have you created that HCat variable to start with?
Yeah, it's in the data editor. The tab command works.
Yeah.
All the subpopulation command works.
So Brian, one thing to make sure is that you have an up-to-date version of Stata. So during the break, we looked at, like, Jupiter was showing me his, I think he was getting a similar error message. He was using version 15 of Stata, which is now considered obsolete. And they changed the syntax for lincom, I believe, in version 17. Yeah. So if you're not using at least version 17 of Stata, you would be getting an error message trying to run that syntax.
I'm just using the license that the class provided.
Okay, then I don't really know. If you're using the syntax that I was illustrating here, it should be working. So I'm not sure. I'd have to see, the code that you're using and everything else. So.
All right.
Maybe Brian, just send me an email with the sequence of code that you're running and the error message that you're seeing, and I can take a look at it.
Okay. All right. Thanks.
Yep. Thanks. Okay. Any other questions? Yes.
So here I can see the output we are having for the R. So we are having the labels of each category. Right. But this is not the case in Stata.
Right. So remember previously in Stata, I showed you guys how to add labels. So you'd have to do that first because we didn't redo that today. So that was in lab 2. In this particular lab, I was showing you how to do that within R. So you have to add those labels within Stata. Okay, I think we're all set. If there are no further questions, so everybody have a good weekend. If you guys are looking for something fun to do in the area, my city, Dexter, is having its 200th birthday celebration over these 4 days. So today, tomorrow, and Sunday in Dexter, which is only about a 10-15 minute drive from here, there's going to be a huge carnival and all kinds of food trucks and all kinds of stuff going on downtown. So if any of you can travel around, be something worth checking out. We'll definitely be checking that out with my family. So just something fun to do for the weekend. So if anybody's interested. Thank you. Okay, thanks everybody. We'll see you on Monday.
Thank you.
Yep. Like this, so what we have right created some operations on the pool of 37,000 NTCs. The population size is coming up with the same. So for this.
I'm guessing because those cases don't have any weight.
Yeah, they don't have any, yeah, so they have like 0 weights. So that's why the number is, so this is fine. So the next thing is like I started working on the next phase, like I did the products in the previous section. I'm going to have score tests for the 2 variables. Like I'm having my independent variable and one by one I checking the association.
This would be backwards though. So if this is your dependent variable, you want to flip these around. So you want that to be your row variable, that to be your.
This is the way. So we need to check the association between the independent variables.
In preparation for regression, yeah, you just want to get a basic sense of whether there seem to be bivariate associations between each of these, and then that can inform how you build your regression.
So the last part is this, having trouble to get having error.
Did you download it and install it?
Yeah, installed, but like I have the values of child labor is 0.134 and the other.
Are those the actual two values on child labor? It's coded 1 and 2. You're sure those are the values if you do a tab on child labor?
Let's go to the next thing.
Yes, it's not 1 and 2, it's 0. That's why it's in there.
Okay, so if I put here.
Assuming there's no overriding issue.
Yeah, that was the problem. Yeah.
Yeah, those numbers in the recode command have to match the actual values.
Thank you.
So when we use the bootstrapping instead of generating
Yeah. You just remember that it's going to create kind of the raw bootstrap weights, and they're not going to be calibrated or anything. So if you want to, you can definitely say type equals bootstrap if bootstrap replicate weights are available, or if you want to create that.
And what about the time for your youngster celebration?
For time, you mean like the days?
And the days, and what is a good time to?
Oh, good time, anytime. It's running all day, all these days. So there's people there right now.
Because in the last couple of weeks ago, we went to the youngster. So it was a very nice place.
Yeah, it's a really beautiful city, but like it's going to look very different now. Like the carnival has basically taken over the entire town, so there's like many roads are closed off and everything. So, but yeah, that's what's happening now. So, yep. And that's where we'll have the 4th of July party. So, yep.
So last time we went for like already. Yeah,
Yeah.
Grocery
Cool.
store already.
Great. Yeah, great.
Yeah, farms too. So Professor,